Okay, so where did we end last time? We were looking at linear programming, right? We talked about like what is the standard form of a linear program, right? We looked at an application, which is max-flow can be just a linear program. And then all we have to do is really plug in your max-flow objective and constants into a helper solver and you would be able to solve it, right? And then we talked about the very important idea of duality, right? Now, duality is a really important and powerful technique in algorithms. I mean, we won't be able to cover the full extent of its power, but we'll just kind of give a glimpse of it. Okay, so the topic for today is kind of try to quickly cover kind of an application of duality, and then I want to spend the rest of the lecture talking about some approximation algorithms. Okay. Now, so the application of duality that I want to talk about is max flow. Okay. Now so in class we saw an example of a standard form linear program, and we knew the recipe of taking the dual, right? So when you apply this to like an algorithmic problem like max flow, and you want to take the dual, there is, in some sense, there is an art to it. Like you need to kind of like structure your problem or LP in a form such that it is easy to take a dual. Otherwise, your life will be really hard, right? And now the max flow problem, like what we saw in the previous class is one way of like formulating it as a linear program, right? Where we looked at, basically what we did is we looked at an edge view of the max flow, right? We had a variable for every edge, right? So that's kind of an edge view of the LP where the variables are a flow variable for every edge, right? And then we do the flow conservation constants and the capacity constant, and we have the LP. Now, as it turns out, if we take that and try to take the dual, you can take the dual, it's going to be cumbersome, but it will be hard to kind of interpret the dual, right? So I hope you see where I'm going with this idea of duality for max flow. Like, can you guess what we are trying to do with taking the dual of max flow? Based on what you know about max flow algorithm or
guessing main cut has some.
Exactly. So when we take the dual, we want to interpret the dual as solving the main cut problem, right? So if you take the dual of the standard edge-based view, the dual would seem like really foreign to main cut. But if you take a different viewpoint of it, then you can actually see that it actually looks like a main cut problem, right? And there are some, so the full like the full gory details of this is going to take a lot of time, so we're just going to look at a sketch of it just to get a feel for the idea, just to give you just to understand that like there is a lot of beautiful connections with linear programming and algorithms, right? Now, what we are going to try to do is take another view of LP, which is the path view of LP. And in some sense, this is a bit more natural view of LP. So a more natural view of the max flow LP. Why? Because if you remember the first or even the greedy algorithms approaches for max flow, we were trying to find one path from S to T, right? And we would try to find the bottleneck on the path, and we would assign that same bottleneck flow on the full path. So in some sense, every ST path gets an assignment of a flow, which is the same flow on all the edges of that path. So I can just basically say that I'm going to now assign a flow not to every edge, but to every ST path in the graph. So that's my viewpoint, right? So let's say let like P, I'm going to define P to be all the ST paths in the graph. Okay, all the ST paths in the graph. And now we know that in general in a graph, if I try to count the number of ST paths, it's going to be exponential. There's going to be a lot of paths in the graph, right? So what I'm going to do is basically now I'm going to assign a flow variable to every path. Okay, so my flow variable is a variable xp for all path in P. Okay, what does this look like? Just to give an example, right? So I'm not going to draw the capacity just to give an example, but there is going to be one path here, right? And then I can say that path is 1. That means I get flow 1, right? Flow 1 across this edge and this edge. That's a flow path with value 1. And then I can have another flow that goes through here, and that could have value 2, right? And now if that path has value 2, that means the total flow on this edge is what? 2 plus 1. The other path also carries 1. So now it's a flow per path. But for example, here, this path and this path share one edge. Sorry, 2 edges. On those 2 shared edges, their flows add up. So from the path formulation, you can get back to the edge formulation by looking at what are the common edges on the paths and calculating the sum of those flows, path flows for that edge, right? So it's a general and equivalent formulation, right? So now let's think about this is what will be the LP in this case, right? Yeah. So now in this example, there is going to be another path here, right? Another path that goes through here. Let's say that is flow 3, right? And now in this case, what is the total flow out of the source vertex? 6. It's 2, 1, and 3. So we assign flows on 3 paths, and we added up the flow for all these 3 paths. And these are ST paths, which mean all those paths start at S, right? So if you sum up the flow for every path, that is what we want to maximize, because they are all starting from S or going into T. It doesn't matter, right? So that means my objective is now going to be to maximize summation for all paths in my set of paths P, which is all the ST paths in the graph. You just maximize the flow on that path. Okay, and then I have a constraint. What will be my constraint? In the original edge-based formulation, I had a flow conservation constraint and a capacity constraint. Yeah. Right? Now, in this formulation, do I need a flow constraint? We don't need a flow constraint. Why? Because we are assigning flows for every path. And for every path by itself, right? So for example, if this is one path, every path gets assigned one flow value. So it's 1, 1. That means for each path, I'm already making sure that the flow is conserved at every edge. And similarly for every other path is the same. So when you add up all the paths to get your total flow, the paths by themselves are already flow conserved, so the total graph is already flow conserved.
What is the input into our linear program?
So the input is going to be a graph with capacities.
Okay.
That's it.
We're not looking at the edge capacities?
The edge capacities are there, and they will come up.
Okay.
Because we still have to have a capacity constraint.
Okay.
But what I'm saying is that the flow constraint is actually kind of embedded in this formulation of having a flow variable per path.
Yep.
Right? And now the capacity constraint will come up in the actual LP constraint, right? And what is the capacity constraint? We know that the capacity of the graph is every edge has a capacity.
Yeah.
So for every edge, what I have to do is that I need to see what are the paths that flow through that edge, and all such paths will have a flow value. I need to add up all those flow values and make sure that it doesn't exceed the capacity.
Yeah.
Right. So that's my capacity constraint. So what I'm going to do is that I'm going to say I'm going to have a capacity constraint which is the capacity of every edge. Let's say this is the edge E, and C of E is the total capacity of that. So we'll have this for every edge in the graph. And what is it? I need to sum up the flow of certain paths, right? But for this constraint, it's not all paths. It's only the paths that pass through the edge, or every path for which E is an edge on that path. That's the same way of saying it. And the way we can write is that this is going to be for all. This is going to be, we're going to sum up over P, all the P's there in here, such that, right, the edge E is on the path P. Okay, that's how I write it. Okay, now this is my linear program, and you can see that. And then we also need that we're going to say that these XP is going to be positive for all the paths. That's okay. But now this is my LP, and this looks simpler than the edge-based LP. And there are less constraints, but we are gonna. So you can see that how many constraints we are going to have here. We're going to have one constraint per edge, but the number of variables is exponential because I have one variable per path. So I have more variables than constraints. Okay, and when we take the dual of this, we'll just have the reverse of it. We'll have less variables and more constraints. Okay, but now in this form, it's much easier to take the dual. Okay, and we'll see how that works. Does this make sense so far? Mm-hmm. Okay. So basically, I'm going to write down my primal. In my primal, the variable is xp, right? The objective is to maximize the sum of xc for all p in the set of paths. And my constraint is that for every edge, right, for every path such that E belongs to that path, I'm going to add up that, and I'm going to do less than or equal to C, right? And this is for all E, okay? And now I want to take the dual of this, okay? So if you remember from the theory of duality, what we do, the process is that every constraint gets assigned a variable, right? So let's say I'm going to assign basically I'm going to assign this variable lambda E. So lambda E is now going to be a variable in my dual program. So I have one constraint per edge, and in the dual I'm going to have one variable per edge. Okay. And now, if you recall from the standard form, it was C transpose of X, Ax less than or equal to B, X less than or equal to 0, right? And then here we would introduce like a Y set of Y variables, right? And that goes into the dual objective, which we are trying to minimize. So now in the dual, the variables are going to be these lambda e, right? And what is the objective? The objective is going to be every capacity value times this variable, and because this is max, I'm going to minimize the dual objective. Okay, so this is max. So now I'm going to minimize sum over E, lambda E, capacity of E. Okay? And now the tricky part is kind of thinking about the constraint, right? Now, we get a constraint, so everything flips around in the dual, right? Every constraint corresponds to a variable in the dual. Now every variable in the primal now would correspond to a constraint. So now we're going to have one constraint per path. Okay, and we need to kind of think about that. How do we kind of find that? So the way we can think about this is, so what was the objective of taking the dual? We were taking the dual because if you look here, we are multiplying the upper bound of the constraint by a lambda such that the sum of these linear combinations dominates the objective function, right? And now the objective function looks like this, right? We have x like path 1 plus x path 2 plus x path, let's say, k, right? And this I need to be such, this is less than or equal to, I need this to be less than or equal to like lambda times summation of all paths. Let's say the edges are E1 such that E1 belongs to P, x of P, plus lambda 2 times summation over E2 such that E2 belongs to P, xp, plus dot dot dot. And this becomes less than or equal to lambda 1 times C of E1 plus lambda 2 times C of E2 plus dot dot dot. Okay? And then this is exactly the objective in the dual program, right? And now what we need is that for example, for the path P1, right? For the path P1, all the paths so P1 is a path, and then P1 can appear. Where can P1 appear? P1 is going to appear for every edge on the path P1, right?
Yeah.
So what we need to do is, if you think about what's happening here, so basically I'm going to look at I'm going to try to find, so x for the first part, xp1 has a coefficient 1 here, which needs to be dominated by the coefficients of xp1 in all of these terms. How do I find that? I look for the P1 path here, right? So the other way I can write this part is, this is summation of E belongs to E. For every edge, I have a lambda E times summation of that edge such that E belongs to P, xp, right? And then if you have a double sum, you can always swap the sum variables, right? So if you swap the sum variables, this becomes summation of p, right? And then, so now summation, this is summation of p for every path in p, right? Because the first variable has to be unconditional. And then the second variable is going to be E belongs to that path P, right? And then you're going to have lambda E xp, okay? And then what you have on this side is basically summation of all paths P xp, and then every path has a value 1, and then we have this here, right? And then now if you equate these two parts, what do you get? You get that for all paths, 1 is less than or equal to summation of E belonging to that path P, lambda E. Okay, so now your constraint here is going to be summation of E belongs to P, lambda E greater or equal to 1 for all path in my set of paths. Okay?
Why is it greater than or equal to 1?
Because from that derivation it was 1 less than or equal to the sum of the lambdas. So I just flipped it around. Right? So on this side of the constant I have 1 times xp. I have the sum over all paths 1 times xp. And here I have sum over all paths, this quantity times xp. So I'm kind of equating this part with the coefficients on that part. And then that's 1 less than this, so this is greater or equal to 1. Okay, so now that's my dual. And now, so let's write down the dual again. So dual is summation of E, lambda E, C of E, minimized such that summation of E belonging to the path E, lambda E greater or equal to 1 for all path graph, right? And then these lambda E's, I want them to be equal to 0. Okay, that's my dual. Okay, and now you can see at least it looks like a capacity, kind of a top capacity problem, right? Because these capacities can come up here. We have a mini here, which looks good. Looks like a minimization problem. And now basically we need to kind of think about how to interpret this, right? And to interpret this, I'm going to make a leap of faith here. And what I'm going to do is that, so I know that these lambdas are generally any positive number. Okay. So now, for the sake of interpretation, but there is a rigor to this, is that just for interpreting it, I'm going to assume that the lambda E is only going to be 2 integer values, 0 or 1. Okay. So I'm kind of enforcing a constraint of these lambdas to be only 0 and 1. Okay. When you do this, when you take a linear program and say that the variables actually are not real numbers, positive real numbers, but they can be only integers, then what you get is called an integer linear program, or an ILP. Okay. And an ILP is generally harder than linear program. Okay. And it's actually NP hard. Okay. And we'll actually see that is NP hard with a simple example. There's a simple way of showing that, right? What we'll actually do is that in the last class we saw the vertex cover was NP hard, right?
The vertex one.
vertex cover. Vertex cover was NP-hard. So if I can give you an ILP formulation of vertex cover, what does that tell you about ILP?
It's also
It is also NP-hard because I'm taking an instance of a vertex cover and reducing it to an instance of an ILP. So it has to be NP-hard. Okay. So that's basically the proof that ILP is NP-hard. Okay. But now with this constraint, we find it's easier to interpret what's happening here. So I'm going to force them to be integers, right? And now when I force this to be an integer, I can now make a choice for every edge, right? To interpret, I can make a choice and say that when I solve this program, right, then some edges are going to be getting a value of 1 and some edges are going to be getting a value of 0. Okay? So basically, I'm going to say that if lambda of E equal to 1, then E is in the cut. Right? What I'm trying to do is I'm trying to solve the cut problem. Right? What does the cut look like? It's basically if S is here and T is here, it's all the edges that pass through the S component and the T component. Right? Basically, we partition the set of vertices into A and B such that S is in A, T is in B, and all the edges that pass from A to B are in the cut. So now this means that for these edges, I'm going to choose lambda E to be 1. And for an edge that stays inside A or stays inside B, or goes from B back to A, they're all going to have value 0. So my mean cut problem is trying to choose a cut. And then I choose a cut by assigning edges in the cut to be a value of 1. So that tells you that a feasible solution to this problem is actually a cut in the graph. Right? And now I need to tell you that so when I choose a value of 0, 1 for every edge, right, I'm kind of constraining a set of edges to be special. But for them to be a cut, we need to utilize this property. Okay? Now what does this property tell us? Right? This property tells us that for every path from S to T, right? What does this property tell us? For every path from S to T, this sum has to be greater than 1. Okay? So that sum has to be greater than 1, and we know that the value for lambda can only be 0 or 1.
Yep.
So, for example, let's say this is S, and this is like one path to T. So this is a path. And for this path, the sum of all edges has to be equal to 1, and lambda E is 0 or 1. Then what can we say about the value of lambda on the edges of this path? What can we infer from these two constants?
That one of them has to be 1.
At least one of them has to be 1, and that's the one that we choose to be in the cut. Okay, so let's say, for example, this one is 1, and these are all 0. And this has to be for every path in the graph.
Right.
So now I can choose another path. Let's say this one, right? And then let's say for that one, this is 1, right?
Okay.
And now this we can do for every path from S to T.
Are you choosing one specific edge? Yep.
I need to choose at least one edge to be 1 for this
You can choose
constraint.
multiple.
I can choose multiple. I can even choose this one, it doesn't matter. Right? But now what you see is that, let's say this is the last path, and I choose this one to be 1. And then you can choose more, but I'm just going to choose 1, that's fine. For the constraint to happen, it's okay if this is equal to just 1. Okay, that's fine. But now, so that means in my cut, I'm saying that these are the edges in the cut. These are the edges that I've chosen to be 1. And now, if I choose these, the question is this a right cut?
Yes,
of the
because
graph?
it
Right?
cuts every path.
It is, right? Because we've chosen one edge for every ST path in the graph. And now, if you remove all these cut edges, you will be disconnecting the graph from ST. There is no path from ST. So it is a cut. So that means a cut is a feasible solution to this LP. Okay. And then what is our objective function?
It's to minimize
The objective function is to minimize the sum over all edges of lambda e CE. And we know that lambda e either 0 or 1. So if it's 0, then it doesn't contribute. But then this is going to be kind of a sum of like all e such that lambda of e equal to 1 and CE. So basically, if it's all these edges that I've chosen to be 1, and we know that this cuts the graph, and then this is then for all those chosen edges the sum of the capacity of the edges in the cut, and then we're minimizing that, so that's the mean cut. So the objective of this dual is to find a mean cut, and that's what we are, and that's why this is a mean cut problem.
Okay.
Okay. And now the only gap that I have is that actually the lambda is can be fractional. But for the integration purposes, I'm saying it's an ILP. So there is a bit of a gap there, but that's the intuition of how the max flow and the mean cut are equivalent of each other, right? So if you solve this mean cut problem, you're going to get an integer solution, but it can be a floating point solution. But in general, if you do the max flow and solve it, you get the max flow, and if you take the dual, you get the mean cut. Okay. So and this is also another proof of the max flow mean cut theorem. Okay. All right. So there is a bit of a gap, and I'll share some notes. I mean, I'm not going to quiz test you on the regular details of this, but this is just to give you an intuition of power duality. Okay. All right. So that's the application of duality. Okay. And now let's talk about another very interesting topic, which is approximation algorithms. For NP-hard problems. Okay. Now, this is another fascinating and very broad topic, so we'll just touch upon a few things. I think I'll be able to cover 2 approximation algorithms, not more than that. But what's the motivation of this? Like, if you recall, we know that NP-hard problems are in general hard to solve, right? We know that the intuition of the set NP is that it has problems that usually have an exponential number of choices, and there is no shortcut. You have to try all possible choices. That's why they're exponential, right? So we have to give up of finding an optimal solution for them. So what is the compromise we can do? One compromise is that, okay, we don't need the exact optimal, but we are okay with something that is maybe good enough, right? So the quality is lower, but we can get it faster, right? So that's usually the trade-off, right? If you want to maybe solve something exactly, maybe it takes a lot of time, but if you're okay with an approximate answer, maybe you can get it quickly, right? So that's kind of the idea. So if you, for example, recall we had the vertex cover problem, right? Do you remember the vertex cover problem definition?
not quite.
Okay. So it was, we are given a graph, right? And we want to find a subset S such that S covers all edges, right? It's the smallest set of vertices such that for every edge, at least one endpoint is in that set, okay? And now, let's say for a particular graph, the optimal vertex cover turns out to be 3. But to find that, you have to spend a lot of time, right? And let's say you have a graph with 1,000 vertices. The optimal is 3, but the exact algorithm takes exponential time. But let's say I give you another algorithm that says that, okay, if the optimal is 3, I can guarantee that my solution is not going to be worse than 6 or double. And from 1,000 vertices, if you get a cover that is size 6, that's not that bad compared to 3. It's just twice as bad. So that's the idea of an approximation algorithm, is that you're going to get a faster algorithm, and there is a bound on how worse your solution can be compared to the optimal. In this case, for example, the algorithm that you'll see is going to be twice as bad. Okay? So the way we think about this is, we say that for example, let OPT be the optimal solution to a minimization problem. Okay, so vertex cover, for example, is a minimization problem, and let's say OPT is the optimal solution to the minimize problem. We say that an alpha approximation algorithm. We say an algorithm is an alpha approximation algorithm let's call it algorithm A. It guarantees that let's say the solution of A is at most alpha times the optimal solution. Okay? And then in this case, let's say alpha is a positive number greater than 1. Okay? So for example, for vertex cover, if this is the optimal number of vertices in the vertex cover, and then let's say alpha is 2, then this says that my heuristic approximation algorithm is guaranteed to give at most 2 times optimal solution. So if you can design the algorithm in such a way, then that's a correct approximation algorithm. Okay? And now our goal is to kind of to see how we can find such a an algorithm. Okay. So now so I want to show the application of LP to solve this problem. Right? There are 2 ways to kind of derive a 2 approximation algorithm for vertex cover. So we'll look at the LP way of doing it. Okay. So now what I want to do is that I want to cast vertex cover as a linear program. Okay. How do I do that? So if I have a graph, right? I have a graph, and what is the solution to a vertex cover?
It's all the vertices that cover all the edges.
Right, but the solution is like a subset of the vertices.
Yeah.
So it's kind of like the min cut. We were choosing this lambda e and saying that lambda equal to 1 means I choose that edge 1, choose an edge, and lambda equal to 0 means I don't choose that edge. So it's a similar case here. I can assign a variable for every vertex, and if the variable is only 1 if I choose that vertex to be in the vertex cover, and 0 if I exclude that from the vertex cover. Right? So that's going to be my strategy, is that I'm going to say that for all vertex in my vertex set, the variable is xv. Okay, xv is my variable. And now notice that I am constraining this variable to be an integer, because my choice, I have two choices. One, I choose the variable, I choose the vertex, or don't choose the vertex. If I choose it, x is 1. If I don't choose it, x is 0. So this cannot be a, at least now, for now, I don't want it to be a fraction. My problem is constraining the variables to be integers, right? So then I say that xv equal to 1 if v is in my chosen vertex cover, and xv equal to 0 otherwise. Okay, right? And then if I that's my variable definition. So in a linear program, in this case it's an integer linear program, I have to define the variables, then I have to define the objective function. Right? So what would be an objective function for vertex cover in this case using these variables?
Minimize x, the summation.
Summation, exactly. Summation of all variables. Very good. And this would basically just mean this term will turn out to be the number of chosen vertices, right? Because if it's not chosen, it's 0, so it doesn't contribute the sum. But if it's chosen, then it contributes 1 to the sum. So I add up all the ones, I get the count of the, I get the size of vertex cover, right? So this will be the size of VC, and I'm trying to minimize that size, right? And now I have to think about what are the constraints. Okay. The constraint now, again, for linear programs on graphs, right? Typically you have variables for vertices and constants for edges, or vice versa. So if you have variables for vertices, our constant will be on edges, right? So now, what is the for a vertex cover? What is the constraint on the edges?
The constraint is that every edge has to have at least one vertex that's
one of the covered vertices, right? So let's say we have this edge in the graph E1, right? And if this is vertex 1 and this is vertex 2, right? Then 1 has the variable x1 and this has the variable x2, and then if this edge is in the graph, then at least one of these needs to be chosen. So if both of these variables are 0, then I haven't chosen anyone. So that's wrong. But if I choose this one as 1 and this is 0, that is okay. If this is 0 and this is 1, that is also okay. And if both are 1, that is also okay. So how would I write the constraint for this edge?
U plus V has to be greater than
Exactly. XU plus XV. So the constraint is that XU plus XV greater or equal to 1 for all edge UV in the set of edges, right? And now that's your linear program for vertex cover, very simple linear program. But we have this constraint that each x has to be 0 or 1, right? So each xv is 0 or 1, and then that's why this is called an integer linear program or an ILP. Okay, and then as I said, we already know that vertex cover is NP hard, and we show a reduction from vertex cover to integer linear program. So this is a proof that integer linear programming, which is linear programming where your variables are constrained to be fixed integers, that is an NP-hard problem. Okay, so this proves that integer linear programming is NP-hard. Okay.
This means that every interlinear program is NP-hard?
Yes.
Wow.
Any interlinear program is NP-hard.
Sounds like really powerful. Like if you can class that as an interlinear.
Interlinear programs, a lot of problems in like graph algorithms turn out to have a ILP formulation, and they are all hard problems. So for example, there is a problem called max-click. I don't know whether I've talked about it. But max-click, or what independent set, of course, will also have a ILP formulation, right? Because it's going to be hard. In some cases, it might be hard to find the formulation. In some cases, it's easy, but there is always a path from any like hard graph problem to an ILP solution. Okay. So now we know that. So this all adds up. Like we know vertex cover is NP-hard. This should not be easy to solve. If it was easy, then vertex cover would also be easy. We know that's not true. So now we need to kind of like relax something, right? So we know that. Well, now we know that ILP is NP-hard. We just proved it. But we know that LP. What is LP? LP is linear programming, which means that the variables don't have any integer constraints. So they can take any real number, like a positive real number. We know that LP is in P, right? The ellipsoid algorithm, we didn't cover it, but that proves that LP is in P, right? So now if I give you the vertex cover ILP, and you want a fast algorithm, what type of approximation can you do here?
You can try to turn it into a linear program.
Yes.
Let's see how it's done.
So ILP for VC, I want to get an L linear program for VC. How do I do that? There is only one way, right? This is the definition for this. ILP is that the variables are integer, and LP the variables are not integer.
So you have to make a mapping from integer to real number.
Right, you just have to relax them to be to allow them to be real numbers, right? So this is kind of a relaxing constraint, relaxation. You relax the ILP into an LP. Okay.
But then the problem changes. It's no longer a vertex cover problem. If you relax the constraints.
Yes.
Okay.
But then once I relax it, I solve it, right? So what happens? The first thing that I'm going to do is I'm going to relax it. So here in the ILP, XP is 0 or 1. Okay? And if I relax it, what can I do? I can say that, okay, I just say that each variable is between 0 and 1. So it can be like 0.5, 0.6 or anything. So if I do that, now LP I can solve it in polynomial time. But then this is not a valid vertex cover, as you pointed out, right? But then I can apply a rule, right? So now I can apply a rule here. So once I solve the LP, what will I have? The solution would be I have a value for each xv, which is between 0 and 1. That's my LP solution. Right, so for example, I can have a value of the vertex 1 can be 0.7, right? The value of 2 can be 0.3, 3 can be 0.6, 4 can be 0.2, right? But now, as you pointed out, this is not a valid vertex cover. But for the vertex cover, I need these to be 0 or 1. So if you have these fractions, what would be a natural way to convert this back to 0 or 1?
Round them.
Rounding, exactly. Okay. That's it. So we just round them back. What is rounding? 0.7 becomes
1.
If you do rounded, 0.7 becomes 1. X2 becomes 0. X3 becomes 1. and x4 becomes 0. Okay? And now that looks closer to a vertex cover, which is a subset of vertices, because we are choosing a number of vertices, right? And we are kind of excluding a number of them. But we know for sure this is not going to be optimal. Okay? But the first thing so this is basically, this is our approximation algorithm. Okay? My approximation algorithm or approximate solution is, I know ILP is NP hard. I cast it, the VC problem as an ILP. I relax it to be a linear program. I solve the linear program using ellipsoid. Theoretically, I need to use ellipsoid because that's the guaranteed polynomial algorithm. But in practice, I could use simplex if I'm solving this practically. And then I get a solution which is fractional, and then I round it. And now this represents a proper subset of the vertices. So that's one thing. But we don't know yet whether it's a vertex cover. Okay? Now, how do I guarantee that it is a vertex cover?
Because if those were vertices in the LP, then we know that every edge that was touching that vertex has to have.
Right.
If it's over 0.2, your vertex that's in the vertex cover, then
Right.
the neighboring vertex had to be
0.8 or something.
Yeah.
That's exactly correct, right? So if I have an edge u to v, and then my LP chooses x u to be 0.2 and x v to be 0.2, right? Then you add them up, xu plus xv is equal to 0.4, which would violate the LP constraint. Because the LP, even though we relax it, xu plus xv still has to be equal to 1. That means at least one of them has to be greater than 0.5, right? And that means they will be rounded up to 1. So for every edge, I'm going to have at least one vertex in the set of values that I am choosing to be 1 in my approximate solution. So that means that I am guaranteed that if I do this process, I relax it to an LP, solve the LP, and do the rounding, right? That rounding is guaranteed to give me a vertex cover. Okay. Okay. So we argued that the rounded relaxed LP is a feasible. It is a vertex cover, right? But what we also, so now we know that if you run this solution, it's going to be fast because it's an LP, and we know that it gives us a valid solution, but we don't know how bad it is compared to the optimum. So we need some guarantee on that also. Okay?
Can we take a break?
Oh yeah, let's take a break. We'll go back here. Okay, should we resume? All right. So now is the big question is, how do we know how bad is this compared to the optimal? Okay. So this is where we're going to utilize linear programming, the ideas, the notion of a linear program, right? So what have we done? Like we have a ILP. Okay, originally it's an ILP is for the vertex cover, right? It's like this. Let's say summation of v in the graph xv. You're going to minimize this such that xu plus xv is equal to 1 for all uv in the graph, and x of u is 0 or 1. Okay. And now we relax this, right? We do a relaxation and we get an LP. What is the LP? It's a relaxation and it's a different problem. It's a different linear program, separate from the ILP. They are connected, but it's a separate program, right? So it's going to be basically the relaxation of this, and I can call it like this, x. I'm gonna, because it's a relaxation, I'm just gonna use a special symbol for it. I'm gonna call it x hat v, such that x hat u plus x hat v is equal to 1, and x hat u is now between 0, it's between the range of 0 and 1. Okay, and this is an LP. Okay, so now let's think about the connection between these two, right?
Sorry, I have a quick question.
Yeah.
Is the linear program, is it okay that we're limiting from 0 to 1, or would we want the entire range of real numbers included?
It's okay to be 0, 0 or 1.
Okay.
In general, the standard form is that x is greater than 0. But when I say that x is also less than 1, it's just an additional constant.
I see.
And that's also linear constant. So you're still, even with this, basically if you actually write this as a pure standard form, you would add that all the xi's are greater to 0, but you would add an additional constant that every x is less than or equal to 1. And that would go inside the matrix A is less than or equal to B, if you think about it, where just one variable has 1, everything else is 0.
Okay.
It's like a capacity constraint. Okay, that's a good question. So now I want to kind of think about, if I solve this ILP, right, I get a solution which is minimum for this problem. And if I solve this LP, I also solve the minimization problem and I get a minimum value. And now my question is, which of these is smaller?
The result.
Yeah, which of these? So if I solve both of these problems, I get an answer, right?
Yeah.
I get an optimal. I get optimal solution for the ILP. I get optimal solution for the LP. Two numbers. I want to know which one is smaller. We are trying to minimize, right? Which one gives you a smaller number? Let's go back to thinking about a picture. Okay. So if this is the picture of a general feasible region of a linear program, right? It's all possible solutions bound dependent on this region or a polynomial, right? Now, if I think about an ILP, right, or any linear program where I've added the constant that my solution, my variables can only be integers. That means the variables can only be at certain grid points. If you think of this as a two-dimensional plane for the sake of simplicity, I'm going to draw these axes. Then you can only pick a solution that is like a grid point in your page, right? So like if this is your grid point, then like it's going to be like something like this. Right? So it's feasible, but also I have the additional constraint that my variables can only be integer, which means that I can only choose these types of points at a certain distance from each other. So when I'm solving the ILP, if this was a feasible region, then I can only choose from these grid points or lattice points to find, across all these grid points, I have to find the minimum grid point, and that will be the solution to that ILP. Okay? But if I relax and solve an LP, then I can do the minimum from a matrix, because all the real points, like these, there are a limited amount of points between these four points. I can also find further minimum from there. So basically the LP is in more power to deliver on the ILP. So if that's the equation that if I relax it, the relax optimization solution is going to be better than the original. So if you can minimize the lower objective function value compared to the locus function. Okay. So that means that, let's say the optimal solution for this is the solution is x_v star, so that the objective, the NP objective is going to be summation for all the x_v cap, let's say juice star, that's the solution. And then for here, the optimal is summation of the x_v star. Now this is going to be greater or equal to because the NP gives me more chance to minimize square. Okay. So that's one thing. Okay. And now once we get the LP, we now do the rounding. Round. What I do in the rounding? In the rounding is where, so x star, right? If x star is greater than equal to 0.5, then basically I round it to be, let's call the rounded variables just z, just for the sake of argument. So that's going to be 1. And if x_v star is less than 0.5, then I get star equal to 0. Right? And now yeah, I'm just confirming something. Now I need to basically compare the sum of these things with, so what do we have so far? So I have that that's more optimal. Right, that's going to be more optimal than my ILP. No, it's more optimal score. It's minimization problem, so that's right. Okay. It's minimized. Right. Yeah, good catch. Okay, thank you. And now, let's see. I think from here, right? What can I say about this I just think the connection between the relaxed program levels and the rounded levels. Rounded levels there's going to be a 2 here, right? Somehow we're going to get a 2 here. Also, yes, because it's 0.5 that makes sense. Right. So, yeah, basically, it's this one here, right? So, this is so basically because we're 2 times basically star E is going to come to 1, right? And then if this star is equal to 1, then this is equal to ZA star. And if it's less than 0, then ZA is 0. So you sum this out, you get 2 times summation of V x to V star, right? And then it's going to be equal to summation of V Z V star. And this is fine because there are some facilities there. So if the amount is 0, if this one is less than 0.5, but if it's 1 or 2, it's going to apply to this right? So this is fine, but that means that so basically what I can do is now I can turn this around. So now this is my final heuristic solution, right? So this is my final kind of rounded objective is summation of V is equal to star, and if I round it around, it's basically equal to 2 times summation of V star V star. But then from here, I know this is equal to 2 times summation of V x V star. Okay, just comment on this way. And this is my algorithm, which is relax the LP and round it. So this is what I'm proposing as algorithm. And then this, what is this? This is our original line. This is the exact line. So if this value is we call optimal OPT, right? Then one of the optimal value for the algorithm has to be less than or equal to 2 times the optimal. So this gives me a exact upper bound on the performance of the algorithm. If optimal is 3, then I'm going to be at most Vmax plus round LP is a new approximation for vertex number. So that's so you see that it is basically just it's a once you know linear programming is called vertex. You do after the vertex and then you get a nice approximation. Now not all approximation algorithms are really this easy, right? There are much harder approximation algorithms. In some sense there are problems that are going to be even hard to approximate. So in this case we make a problem under approximation algorithm. And this is also known as the GPAs, fundamental approximation scheme. Right? But there are problems that are even hard to approximate. That's another whole beautiful theory when we really have these about the hardness of approximation. Right? So there are problems that are even hard to approximate. And then that's really beyond our course. Okay. So that's our first example of an approximation algorithm. Any questions on this so far? This makes sense. Is the data over program for vertex color that we have is the vertex color for fraction solution. The fractional linear program in this case is not a vertex number. So it's not a hard LP in the sense that it doesn't take a lot of space. Right? It's the space is what? You have like that number variables is V. The number of constants is you have a problem with that. Right? Whereas the next problem in the space the next problem is space and so that may not get really polynomial space in there. You know what I like to encode that. So let's look at another. So we look at. So we know from previous lectures that how to get the R and the problem is R. So let's think about an approximation algorithm for some other NPR problems. So what is the other kind of important NPR problem that we know of? What will we choose? Choose that. Yeah. So there is a kind of so 3-sat, remember, is where you have these bunch of normal problem with cross 2 rows, choose one of those and one of the 3-sat. Now 3-sat has a variant, right? It's called max-3-sat. What is max-3-sat? In 3-sat, we have to satisfy all the clauses. Right? Max-3-sat says that I will not satisfy all the clauses and maximize number of satisfied clauses. So if you have 10 clauses, then you can satisfy 7 clauses. But you want to find an assignment of variables that maximize the number of clauses that you can satisfy. So if you can satisfy all of them, then you are solving 3-sat. But if you try to satisfy the maximum number of things, then it's max-3-sat. doesn't make sense problems. But it's also hard, right? Because if you solve max-3-sat in polynomial time, right, you can use that to solve 3-sat. Right? You just check whether the number of clauses given by max-3-sat is equal to the total number of clauses. So it's right. So this is also hard. Which means we can think of trying to find an approximate solution for this. Now, compared to vertex cover, this is a maximization problem, right? So then we want to find if you want to find an alpha approximation, for max 3-sat, here alpha is going to be less than equal to 1. Right? Does this make sense? When alpha is less than 1 for maximization problem, right? Because if alpha is 1, that means it's going to be the wrong problem. That's kind of because it's maximum. So if alpha equal to 0.5, then basically if your algorithm is A, then you want the value of A be greater or equal to alpha times optimal. Okay. So just a reverse of the numerical problem. Okay. So now let's think of a approximation for max-3-sat. Okay. And now let's kind of think of an algorithm for this. So let's say this is my formula. Like it's doing something like x1 or x2 bar or x3 and x4 or x5 bar or x7. A bunch of these clauses, right? Okay. And now I want to find a heuristic for this, right? So what are you thinking of? So it has to be, we cannot eliminate all possible variables, that's not exponential. We know that 3-sat is simplified. So you have exponential number of choices, but is there a simple way to find an assembly that has some performance guarantee? So just to give a hint, this is going to be a randomized approximation. So you have to classify. So the way to classify to any value, how would you assign the value to it? Whether or not so you have a 50% chance you choose 1 and 50% chance you choose 2. Basically it's a fair value, right? So that's basically that's the algorithm. Okay, and we'll see that simple algorithm gives us a nice approximation. We get alpha value equals to 1. Okay, and it's a very surprising idea. But basically this is the algorithm for R equal to 1 to n, right? Then when we set xi equal to 1 with probability 0.5 and set xi equal to 0 with probability 0.5. And that's my algorithm. Okay? And now this is feasible, right? Because every variable there is 0 or 1. So I'm finding the assignment. And then when I have an assignment, I can evaluate and see how many clauses are satisfied. Right? And my aim is that this would give us a good approximation. So whatever was the maximum number of clauses satisfied, compared with the satisfied will be let's say 80% of the clauses. Right? If I compare 100% of clauses, that's the optimal one. So we can get it. So it's going to be less than 1 or less than 100%. Okay? And now let's analyze it. This algorithm. No, right? Like analysis. So the analysis is now what do we know about every clause?
We know that there's 0.5 by 0.5 chance of being bound true.
Almost just the reverse. Right? So basically, if your clause is like this, x1 or x2 or x3, for this to be false, you need all of it be false. So the probability, so this clause was C. Probability of C is false. This probability of x1 is assigned 0 times probability of x2 is assigned 0 and probability of x3 is assigned 0. And that's 0.5 times 0.5, so 1 by 8. So that's the chance that this clause is false. So the probability whatever the C is satisfied. It's just 1 minus 1 by 8 equal to 7 by 8. Okay? Now this is basically not a deterministic algorithm, right? Because the number of clauses that you satisfy every time you use any count the system you can define something. Right? So here we have to talk about the expected value of the expected number of the clauses satisfied. Okay? So let's say that I have clauses. So for each clause, right, let's say each clause Ci, I'm going to define what is called an indicator variable. So if you've done a probability course, you probably have indicator variables. An indicator variable, I'm going to call it, let's say, Z high, okay, and then what I want to say is, so we say that Zi is 1 if Ci is satisfied, right? And Zi equal to 0, otherwise. Okay? And now, what is my objective? My objective is to maximize the average number of maximize the total number of clauses satisfied on average. Because every time I'm doing this, I'm getting a combination of variables that are satisfied, that are 1, right? So basically my objective is this. If I take this one, Zi, right? Now Zi, what is the probability that Zi equal to 1? 7, right? That means this Zi is basically what is called a random variable. Right? Because every time I toss this coin, I get different value for each Zi. Right? And it's 1 with probability 7 hits and 0 otherwise. Okay. So now that means the sum of variables is also a random variable. But then I want to find what is the expected value of average value of this. Right? So now this is what we are trying to find. Okay. But how do and I need to compare this with the optimal. Okay. Now how do I compute this expectation of the sum of random variables?
We did this once.
Let me do the quick select, right? But the kind of the powerful tool is related expectation. Expectation. So if you take a bunch of random variables and calculate the average of expectation, it's the same as the sum of the expectation of each value. This is the most powerful tool from one that you can use in algorithms. So this is going to be just the sum of high expectation of each value. So this expectation is basically just the weighted average of the values. So now I just need to find out the expectation of each zi. What is the expectation of zi? The zi is basically it's 1 equal to 7 bits, right? And so 1 and it's weighted by 7 bits times 7 by 8. And the other term of zi is 0, and that happens with 31 by 8, but that is goes away. So the expectation of this is 7 by 8. Okay. So this is going to be what? It's going to be basically 7 by 8 times 10, where n is the natural number of clauses.
Is that not I in that case?
Yeah, I belongs to 1 to n.
I see.
Because you have one zi for every clause, and the number of clauses is m. Okay, so that means my approximation algorithm does 7 by 8 times 10, right? And now so my algorithm gets performing 7 by 8 of n, right? And what about the optimal algorithm? The optimal algorithm, whatever it does, it's not going to be weighted by time. It's going to be something small by time. Right? So this is going to be some level of 7 by 10, right? And then that means n is equal to optimal. So this is equal to 7 by 8 times the optimal. Right? And that tells us the value of the algorithm is at least 7 by 8 times optimal. Okay, that's a very simple algorithm. But it's almost close to 1. Right? It didn't do that much work. And now there are some really surprising and striking deep theoretical results compared to this. Right? And I just want to tell you the name of this. So now, so this was very, this problem didn't work out. It was a very simple algorithm. So obviously, like instead of saying that time will be not 7 by 8, and it's 7 by 8 plus a smaller sum. Right? But there is a beautiful result known as the PCP theorem. Right? PCP theorem says that the 7 by 8, if you try to at least find the 7 by 8 plus 7 times approximation algorithm for max-3-sat is what? NPR. So you don't have any now. So in some sense, 7 by 8 is almost the best you can do. Because this holds for all epsilon union 0. It means, in some sense, the 7 by 8 approximation is optimal. It's going to become a better approximation like this. The other but it's optimal in the sense that you get the best ratio. You don't do better than that. What does TCP stand for? This is like even beyond me, like I haven't yet fully understood the proof of this, but it's called about realistically capable proof. You should read this as an assignment topic. Alright, I think that's I want here. So I think I covered all that I want to cover. Like we talked about the involved of the max-flow problem about at least for the claim of what is the problem. We didn't fully elaborate because the dual is a fractional LP, but Mincup is an LP. So there is still a gap with the proof there. So I didn't cover that. But we can make that rigorous. Right? And then we also quickly cover two approximation algorithms. And we saw that again linear programming was crucial to find that approximation algorithm. Right? And then the second one was a simple randomized strategy also gives us another very simple approximation algorithm. So I wasn't able to cover too much randomized algorithms in this course. I really only covered two. One was the quick select, right, which was a randomized analysis. And then this is another simple randomized algorithm. But randomizing is really another powerful thing that you can use to have real patterns. Right? Sometimes the deterministic algorithm is extremely hard to have, but you can just replace something, just introduce some complexes or some approximation, and that gives you a very much simpler algorithm. So randomized algorithms are really much simpler, but the analysis you can have because there's always there. But it's another advanced area which is very beautiful and lots of interesting results there. Okay, so that's the end of the lecture. So let me stop this and then we can have some more questions.